Today we're going to talk, or in this session we're going to talk about Postgres-XL. I'll give a little intro, background. I'll talk about the architecture of Postgres-XL, give some examples of how to distribute tables, how that works. I also want to do a short demo to show you how to configure a local cluster on your laptop in case you want to kick the tires on this thing and figure out how it really works. And I can talk about the differences compared to standard Postgres and another project called Postgres-XC, and talk a little bit about the community. So who am I? Mason Sharp. I'm the co-organizer of the New York City Postgres user group. Actually, one of my co-organizers is in another room speaking right now as well. I'm chief architect at Translattice. I previously was at StormDB and EnterpriseDB. Probably a lot of current and ex-EnterpriseDB employees around. I worked on a few different database clustering projects, GridSQL, Postgres-XC, and now Postgres-XL. I wanted to just bear with me for a couple minutes. I wanted to talk about Translattice, my employer, just because, hey, their flagship product is based on Postgres, but a lot of people have never even heard of it or heard of them. So just to tell you a little bit about Translattice, they are a well-funded venture-backed company. Their other flagship product is called TED, the Translattice Elastic Database. Doesn't really have anything to do with Postgres-XL, other than we're applying some of our know-how from Postgres-XL to improve TED. But how many people here today were at Simon Rigg's session earlier? Yeah, a lot. I think there's a lot of interest in scalability. He talked about BDR, which is a really cool feature upcoming in Postgres 9.4. There were some questions at the end about, well, what do you do about commit time and how are conflicts resolved? And he said, well, it's really after the fact. So one difference in TED is it's commit time resolution. So at commit time, it will look for conflicts and decide who wins and who loses. So it's a little bit different in that regard. Someone had mentioned Paxos as a question. Actually, it does use fast generalized Paxos. And TED itself has its roots in Postgres-R. So it allows you to geographically distribute data, shard data as well, recovers automatically, allows you to easily add nodes, etc. Anyway, so that's TED. Now we'll talk about Postgres-XL. Also in Simon's session, I thought he said some good things, some interesting things. Like he talked about, well, to get scalability, sure, you can have these replicas and you can read them and share the reads, but it comes with a cost. You have to write at all these locations. So sure, you have more nodes, but guess what? They're also writing at the same time if you set up your cluster that way. So it's important to know your application. I agree with that too, that you kind of tailor your scale-out solution towards your applications if you can. So Postgres-XL, we announced in May 2014 that it was open sourced. Before getting into details, just a quick flavor of how this might look. I'll go into a lot more detail later. There are many different components in how this thing scales out. But Postgres-XL, it's free and open source like Postgres itself. It's a scale-out relational database. Just as Simon talked about knowing your workload and that it's difficult to scale out for all these different things, well, we try to handle all these different workloads with just this one cluster. There's MPP-style processing. So you can think of it almost as an open source Greenplum, but without the columnar compression, where we get the nodes working together in parallel and parallelized queries as much as we can. But in addition, it also can scale out your write transaction workloads. So we can scale OLTP as well. And while doing that, we ensure cluster-wide ACID properties. So sometimes if you were to try to do your own sharded solution and you have transactions where you have to write to multiple nodes at the same time, it's possible that you could get anomalies where you're trying to get consistency, but you may be, because of transactions committing at different times, you may actually be reading data in an inconsistent manner. So Postgres-XL, its predecessor project, Postgres-XC, one of its main goals was to ensure consistency cluster-wide, and so we inherited that. We also add some other things like multi-tenant security. So if you wanted to take this and do a database as a service, for example, you won't be able to query the PG database table and see what other databases are there and then try and guess passwords and things like that. So that we try to lock that down. And just given its distributed nature, you could use it as a key value store. Use JSON data types as the value. I think one reason why people are attracted to those NoSQL solutions are, oh, I can put everything in memory because I have more machines and all that. Well, you could have everything cached within these Postgres-XL nodes if you wanted to. So Postgres-XL can be used as an HTAP system. Given those different type of workloads I talked about, if you had a hybrid, it can be a hybrid transactional and analytical processing system. I talked to a potential customer a few weeks ago he has Mongodb to power his web-based storefront that they have at his company, and he doesn't like it. And then when they process credit cards, they're using Oracle because they don't want to lose data, and they feel comfortable using Oracle for credit card transactions. And then they have yet another third database for doing their data warehousing. And they had a relatively modest amount of data. I think it was just a terabyte or so. So he looked at this and he said, wow, so I can actually use this in all these cases. This could replace all of those. And I said, that's right. And he said, so that means my staff, they would learn one database platform and they'd be able to use it as effectively a key value store, relational database, and a data warehouse. And he's right. You can do that. In addition, Postgres-XL's query capability, it's not very limited. I mean, there's rich SQL support. Even though it's distributed, it supports correlated subqueries. We spend a lot of time trying to optimize complex queries and handle things efficiently on the network. So more Postgres-XL features. Just as Postgres itself supports MVCC, multi-version concurrency control, we take that and also support that cluster-wide within Postgres-XL. Readers don't block writers, writers don't block readers. We take transaction IDs and snapshots and make them cluster-wide. I'll talk more about that on later slides. It's being based on Postgres. It's contrib-friendly. A lot of contrib modules you can just add and they work. There's full text search, JSON, XML support, JSON-B as we add in 9.4 compatibility and merge that code in, we should get that too. Okay, so far, wow, it all sounds great that it can do all this stuff, but well, there are some things that can be improved. So full disclosure, talk about some of those things. Like there's no built-in high availability. To be clear, you can have a standby for every component. You can configure data node standbys. There's this other element called the Global Transaction Manager. You can configure a GTM standby, but there's no automatic native built-in thing that decides, hey, let's do a quorum and come to a consensus that something is down and fail over. That's not built in. We have used externally the pairing of CoralSync Pacemaker to manage that. It works. It can be kind of a pain. But anyway, nothing like that is built in. The other thing, resharding, that's also something people ask for and that we need to improve. There are things there. Yeah, you can have a live cluster. You can add a new node to it, no problem. But the tables aren't automatically redistributed. So you have to go in and tell it to redistribute the table. And then it's going to be locked during redistribution. So I think for some environments, that's also not acceptable. But these are areas I think we can work on to improve. I think also with Postgres 9.4's logical streaming replication, or BDR, I think there's perhaps the opportunity there where maybe we can, behind the scenes, be redistributing a table while writing to the old copy and then collecting these changes and also later applying them to the new one and rename the table and drop the old one. We haven't spent a lot of time researching that, but anyway, we want to make this easier in the future and improve that. Also, another limitation, foreign keys and unique key constraints. At the moment, you can't have distributed constraints. So what that means is you can have some. So like, let's say you decide to shard based on a column, one particular column that also happens to be part of the primary key. We know that because we know which node that key maps to, we know that we can create a unique constraint on it. And we don't have to worry about the same unique value being on two different nodes. So when we can enforce it, we'll push it down. If we detect we're not going to be able to enforce this constraint, we'll just the command will error out, and the user will know, oh, okay, I can't support this particular one. So Postgres-XL, I have a few outdated graphs. They're kind of outdated. I have started to run some new tests for some things, but just to give you an idea, like say for a transactional workload, we did a comparison against Amazon RDS. This is not the Postgres one, and it's kind of old, just to show, okay, as we add more concurrency, yes, we can scale. I think this was with 4 nodes. We aren't limited to what just one system can do. And then there's another benchmark out there, DBT3, which is based on TPCH, more of a old data warehousing benchmark. And we compared native Postgres performance against 2 nodes and 4 nodes of Postgres-XL. And then here too, as you have more nodes, your query times are going down because we're able to use query parallelism and get all the nodes working and processing the data in parallel faster. One of the things I started testing this week, I ran out of time, was at Amazon EC2. So Postgres-XL, I think it could be useful not just for multiple systems, but even on one system. In Postgres, let's say you have a lot of data. Maybe you don't have that much concurrency, but you have a big server. Let's say it has 32 cores, and you kick off a query. Maybe it has to go through tens, hundreds of gigabytes of data. Well, you're going to have 1 core working and 31 cores idle. You have a lot of unused capacity on that system, which is too bad in Postgres. Now, I know there are some smart people right now in the Postgres community looking at this, which is great. But Postgres-XL, in the meantime, could help fill that gap too, where you can configure multiple nodes on one particular server or VM and get those cores working. So I was doing some tests, say, on a 8 virtual CPU VM and comparing that against Postgres, and I was seeing some good results. I need to publish that, showing that, hey, just split up your data, get more cores working, and yeah, of course you get better performance. We also ran some tests comparing against MongoDB, so using as a key value store. I think we saw some, also earlier today, Mark Linster showed some performance graphs comparing 9.4 against MongoDB. Probably saw something kind of similar. Yeah, so in this case, I think we used 3 or 4 nodes, and we kept adding concurrency. That's the x-axis, and the more we added, the better in comparison, I think, Postgres-XL performed. Okay. So before I get into more details about the architecture and technology, are there any questions? General questions?
Generally, so it's a totally dedicated platform, totally different from Postgres. Is that considered?
Well, I would say, well, some may say, well, it's a fork. I would say, well, maybe it's can be a branch. I mean, we're constantly merging back Postgres, but we are a little bit behind right now. Right now it's a 9.2 code base. We will be merging soon. I'm hoping by the end of the year that we're actually up to not just 9.3, but 9.4, where we go, instead of, say, us merging in 9.3, having a stabilization period, then merging in 9.4, I think we're just going to do 9.3, 9.4, and stabilize and catch up. But yeah, no, we want to try to be up to date. Now, if there's any, say, particular feature we're having a problem merging in, I think what we would probably do is, hey, let's get this out there and just, you know, this particular feature X, whatever it is, it's giving us, that's hard, just given our different architecture, that's hard. Maybe we just disable that particular new feature and, you know, get it out the door and then go back and address that. But yeah, we want to stay up to date. Yes?
The test that you mentioned that you haven't published here, the one that you ran last week, for that to achieve scalability, multiple scalability, did you have to shard the data or was it without any sharding?
Yeah, we created, or I created multiple nodes on the one system. And I did it a couple of different ways where I gave it each a dedicated EBS volume, and then I also did a shared one. Yeah, I need to polish that stuff up and put it out. Yeah, I think there was another one back here.
I just want to clarify, your x-axis on some of these charts was going up to like 100. Is that 100 separate
Oops.
nodes in the system? Maybe all in one box, but like 400 there?
Oh, I'm sorry. No, the, concurrent users on this one. On this one, these are the different queries. There are 22 or so queries. And then this one is also concurrent users. OK? Any other questions, or I'll continue? OK. So getting into some of the details about how this all works and how it looks. So there are some major components. Data can come in from the load balancer. We have multiple coordinators, so you aren't limited to just one. You can keep adding as many as you'd like. That manages the sessions, and then the end user data actually gets stored on the data nodes down there. Then we have this other thing called the Global Transaction Manager, and that's what's responsible for ensuring consistency in the cluster. There's a second one there because it is possible to have a standby ready to go in case you need to fail over. But in any event, so the user sessions, they only connect to the coordinators. And as they insert data, it's going to be spread out amongst the data nodes. And then as they query data, you know, it's going to go back through the coordinators and return to the users. So conceptually, just to make it easier to understand, the coordinators here are broken out as a separate layer, but there really is nothing preventing you from running coordinator processes on the data node systems and just having, you know, it flat. And there are some advantages to doing that too, where if you're reading from a replicated table, for example, it'll just read locally instead of having to go across the network. But you know, your data nodes might be a more expensive class of machine, a lot beefier. So I think it just kind of depends on your workload and cost and budget, which way makes more sense. If you have a lot more concurrency, you probably want more coordinators. If you don't have that much concurrency, you could have fewer. So I think it just kind of depends. Anyway, all the while, the Global Transaction Manager makes sure that you have a consistent view of the data. Going into each of these components a little faster, deeper, I mean. So the coordinator handles the sessions, parses and plans the statements, and it'll do things like merge sort results back from the individual data nodes for performance and things like that. And it will handle two-phase commit. Now, it might be, you can explicitly do two-phase commit, but some implicit two-phase commit might happen. You know, if you do a write transaction that goes to one node, it's just going to commit it there. But if you have two data nodes or more involved in a transaction, it knows it has to do this as a two-phase commit transaction to make sure that it's consistent. In addition, the coordinator contains the global catalog information. Data nodes, again, that's where your end user data really is stored. You don't want to connect to them directly. You always want to go through a coordinator layer. Now in Postgres-XL, we've added in some intelligence where the data nodes communicate with one another directly. So if you're doing a join and data from one table needs to be joined with data from another table on another node, that data is going to be shipped around directly. There's no need necessarily to say, go up to a coordinator and handle it there. So we parallelize the plan once, send it down, and the data nodes just get instructions from the coordinator of how to process the query, if it's going to need to prepare data to be consumed by the other data nodes, etc. So the GTM, in order for us to have this cluster-wide MVCC, internally in Postgres, transaction IDs are used, as well as snapshots. Snapshots are a list of running transactions, essentially. So to make this consistent, we use transaction IDs that are global to the cluster, and the GTM is responsible for handing those out, as well as snapshots. In addition, it handles timestamps and sequences too. We've done some optimizations around sequences so that that's handled efficiently, handing out bigger chunks as we see certain activity from a particular node. So timestamps, like if you use the now function, it'll actually, within a transaction, always return the same value, even, no matter how many statements down you are on the transaction. So what we do is when a session asks for a transaction ID, we just, in the same message, give it a timestamp too. And so that can be used internally further in processing the query. So you might be looking at that and say, well, that sounds great, but won't that become a bottleneck? And the answer is yes, yes it will. We saw that GTM was becoming a bottleneck as we tried bigger and bigger tests, like 10 nodes. And so we created this thing called the Gtm Proxy. It's a process that runs alongside a coordinator in particular. So say 10 sessions simultaneously say begin, or actually would happen at a later time. But anyway, say they need a new transaction ID, 10 at the same time. The proxy collects those as one request, sends one request to GTM, which will then return a range of 10. And that's kind of demuxed back from Gtm Proxy to those clients that requested it. That has a lot of advantages. There's less network traffic going across. Critical sections of code that are responsible for transaction IDs are locked for a shorter period of time because it's doing 10 at once. So this allows us to scale out a lot more different ways. So GTM Proxy, if you decide to try this out and are running tests, please make sure, and you really want to heavily stress it, please make sure that you use GTM Proxy. Talk a little bit about how data is distributed. There are a couple primary ways of distributing your data or how to do it. And I'll show some DDL as well of how to do that. But say some tables you can designate as being replicated. This is really good for your read-only, read-mainly tables. It might be state code tables, things that are pretty static. But even if you have some transaction activity going on, you could consider replicating as long as it's not too heavy. So it's good for those type of tables. It's good for dimension tables and data warehousing, especially dimension that doesn't change very often. And I talked earlier about the benefit of if you put the coordinator and data node process on the same physical server, that it can read this replicated data locally and not have to go across the network. So there's a benefit to doing that too. But replicated tables are really bad for write-heavy tables because it's going to have to write everywhere. If you just have a workload where you load up data once a day and read it all the time, then maybe that's okay to replicate all the tables. And it pretty much works via statement-based replication, and there's a little bit of intelligence in there where it avoids some deadlocks in case there are concurrent writes. So for other tables, it makes sense. You really want to distribute them, shard them as much as possible. So these would be really write-heavy tables in the case of OLTP, or for, say, data warehousing, your really big fact tables. You might as well spread that out as much as possible. So there, instead of a row being on every single node like the replicated tables, it's just going to go to one node. And there are a couple of strategies on how you can specify how the data gets distributed. There's hash, round robin, and modulo. In practice, you should probably mainly use hash, which gets calculated, gets mapped to a bucket, hash bucket, which gets mapped to a node effectively. But there are some other types like round robin. You might have just a table with one column that's a big text column, and calculating a hash on it, it's not really a good key, say. Maybe it's log type data you've collected. You might as well just, you're not going to really be querying it by key, spread it out and use round robin. But I think in practice, most of the time, you'll use hash. That text there is slightly misleading in terms of no single point of failure. You have to configure everything yourself. But something we have done is, like in the case of the data nodes, is to have two replicas where, say you have data on server 1, and you have a replica on server 2 and server 3 of that. But then you also have master data on server 2 and have a replica on server 3 and server 4. So it is possible to create something fairly redundant. And one thing that surprised us in these tests is for write-heavy workloads is when we configured it this way, we only saw a 15% degradation in performance by having two replicas. So that really speaks to just how efficient Postgres' native streaming replication is. We did have a write-back, battery-backed controller card to help us get that type of performance. But anyway, that was a pleasant surprise. And again, failover is manual. You can configure standbys, but you have to manually failover. I'll go into how the DDL looks to create the tables and set that up. But before I do, are there any questions at this point? Yes?
You mentioned before that if you had, say, two tables you were joining in different nodes, it'll do the crosstalk between them. Is it smart enough where if you have two tables distributed on the same key, it won't do the crosstalk?
Yeah, that's right. The planner looks at that. It sees if you're joining, say you have, for example, orders and line item, where they're both distributed on order key, it will examine the where clause, and if it sees orders.order key equals line item.order key, oh, I can push this join down, and I don't need to worry about moving data around. It will do that. Similarly, anytime you join with a replicated table, if that replicated table is local on that node, it too knows, oh, okay, I don't need to worry about shipping data around. I'll just join with the replicated table. So that's really useful for, say, star schemas and things like that. Sorry, I'm laughing. I used to work together, not in the same company, but we worked on this other project, Postgres-XL, together. Yeah, that's actually a great question. We have session identifiers. So this is actually something that's also kind of unique. So even though we have multiple connections coming in, to the multiple nodes. They're actually multiple connections, but we know that they're associated with one another, that they're running with a certain transaction ID and snapshot and command ID. And yes, we handle that. The other related thing we did for that is temp tables were a bit of an issue because temp tables tend to be tied to one connection. We made some changes there where temp tables could then be accessed across these multiple connections and have them associated with the session. Yes?
How is SSI handled?
I'm not sure. Let me get back to you on that one.
Okay.
Yeah. Okay. So DDL. Here's how it looks. You're familiar with create table, of course. So we changed it by adding a distribute by clause at the end. You can specify all those different possibilities I mentioned before, hash, modulo, etc., as well as possibly specify a subset of nodes you want the data on. So here's an example. If you wanted to set up a state code table, for example, distribute by replication, put an exact replica on every node. Here's another example, distributing by invoice ID. It's usually a good idea to distribute by a primary key or a foreign key to, if you're a child table, to the parent. And this kind of gets to a question earlier. What if you distribute by kind of that parent-child relationship that, yes, it's smart enough to see, oh, I can push down the join. Just do a couple quick examples. If I don't know how many of you look at explain output from time to time? Okay, good. Then it's good that I'm doing this. I'll show you what the explain output looks like so you get an idea. All right, so say we got a couple examples, table T1 and T2, distributed by call 1 and call 3 respectively. If we do something like this where we join on their respective distribution columns, you can see that it's pretty much just pushing down the plan. A plan is created once, it's pushed down to the data nodes, and will be executed. The only real difference is it's saying, oh, where to execute this. In this case, I configured a small 2-data node system. But let's say we have something a little bit different. Here, we're using column 2 from T1, which is not a distribution column. But on T2, column 3 is. So the plan looks a little different. After it scans, as it's scanning T1, it knows, oh, since it joins with column 3, which is hash distributed, as I'm reading these rows, I'm going to get it ready to be distributed, and I'm going to hash on this value so that it can move over to where the particular row would be for T2's call 3. So it's going to read and distribute, and then it's going to do this data node communication. So yeah, we went to the trouble of showing what's happening in the explain plan there. Okay, so I thought I would show how to move on to show how to configure a small cluster, like for your local laptop. But before I do that, are there any questions about any of that stuff? Yes?
Do you have a practical limit on the, or a practical or a logical limit on the number of nodes you can have in a cluster?
I think in practice it probably depends on your workload and concurrency. I think you're more likely to hit a limit if it's OLTP heavy, because you have more and more open transactions. The snapshots are getting larger and larger, and also your X-min may be lower and lower, where it may have to do more checking in between in the snapshot. I can tell you at some point a while back, some tests were done on bare metal servers, not VMs, using 10. And the coordinate 10 nodes, the coordinator's at about a 30% overhead in tests we did. So that means ideally we should see, say, 7 times performance with 10 nodes, given the overhead. But what we ended up seeing was like about 6 point something, I think it depended, it varied, it was 6.4 and then it was 6.2. So yeah, it's not quite linear, but hey, if you still need some scalability beyond what one node can do, this can really help. Now for like a data warehousing type of workload, if it's low concurrency and you have a pretty simple schema that's just a fact table and maybe some dimension tables, you really can go far. I don't know what that limit is. If all your data is perfectly partitioned and you never issue complicated queries that have to ship data around, you could have a really large number. Yeah.
Actually, I have two questions. I noticed that you create DDR statement is only just distributed. So it seems like we do not really manage the table space in there, or we just designate certain data, the table to the certain nodes.
Yeah.
Which maybe by hash. And another question, the other question.
Wait. I'm not very smart, so I'll probably forget your second question. So let me answer that one first. Yeah, you can use table spaces. The way you have to set it up now, though, is you have to name it the same thing on all the nodes you want to refer to it as. I think we could maybe in the future make that a little more flexible where different nodes could maybe place it in different places, but have a logical name for it all. But so short answer is yes, you can do it. Second.
The second one is currently the Postgres just run every transaction in a single CPU, a single thread.
Yeah.
So when we go to this Postgres-XL, is that also for when we go distribute the transaction to different nodes, is for every node just pick up one CPU, one thread, or is going to be?
Yeah. Yeah, so each data node could use one of those cores, but you could configure multiple data nodes per server. So if you had an 8-core machine, say, you could configure 8 data nodes on it. Doesn't matter, yeah, whatever you want, yeah. So you can configure multiple data nodes on the same server or on the same virtual machine and then get parallel query parallelism that way. Yes? No, yeah, this is, from time to time, this does get asked. Not at the moment. I've thought about how to do that a little bit, since it does get asked occasionally, but for right now, we're just focusing on doing it locally. I think there are a couple things we could do. We could potentially use Postgres as streaming replication and have replicas somewhere else, and then see if we can get, like right now, your standbys are only warm, whereas in Postgres you can have hot queryable standbys. We can't do that at the moment. I think there's a little bit of work that needs to be done for that to happen. Yeah. Okay. All right, so I thought I'd show, hey, this actually isn't quite as bad as it looks, or as you might think to configure. So show some examples. Again, probably, yeah, don't be scared. It's not too bad. So there's this utility you really should use, and we tried to recently improve the documentation because the old documentation showed all the manual steps had to do it, and these were long manual steps, and if you missed a step, then people email the mailing list and say, hey, my cluster doesn't work. And then you have to look at hundreds or 100 different parameters to try to figure out why. And so I just started saying, use PGX-CCTL, use PGX-CCTL. Because once you kind of got it right, it all kind of works. And there are checks in there where it looks for port conflicts and common things like that. So if you try it out, please use that. And that's what we're going to use here. Otherwise, you got to go through all the manual steps in a GTM and a DB and whatnot, which you can do. And then there'll be, there's some additional variables to configure in the PostgreSQL.conf. There are RPMs available as well. Okay. I really recommend pulling from the Git repository. We've made we've done a lot of bug fixes in the PGXCCTL utility. So check that out, and there are more on the way. It's been an area of focus recently. If you start trying things like failing over, it'll work a lot better. But other things look very Postgres-like: configure, make install. When you set up your environment, though, make sure somewhere you update path to where your binaries are, because SSH is used, and if it doesn't find it, you'll get an error message, command not found. The other thing you should do is set up SSH keys, because, again, it uses SSH, and you're going to be getting, please enter password, password. And it's running command after command as it automatically configures things, so you may get prompted 20, 30 times. But configuring that avoids all that. Okay. So this utility, PGXCCTL, it allows us to initialize, start, stop, deploy. It's pretty handy. I will exit out of this briefly and try to show you how that works. So there's this file, PGXCCTL. There are a series of parameters here. I did have some slides to go through those. I'm getting low on time, so I'm going to step through this kind of quickly. But yeah, basically, maybe this is hard to see. You specify where GTM is, specify you want, in this case I configured one coordinator, what port. Pooler port, we use a pool of connections to connect to the data nodes. It's much more efficient, just use connections when we need. Then we have some additional data node configuration parameters. Just specify, the ports, pooler ports, the servers where those are running. In this case, I'm using localhost. And tell it I'm not going to configure any slaves for this short example. So those type of things. And once we've done that, we just need to run this command, pgxcctl init all. I spelled that wrong. And it's going to go through and initialize all these components. It takes about a minute or so.
It's a one-shot deal, right?
Yeah, but the nice thing is, as you try to configure it, like if you made a mistake, just redo it. Just rerun it. Init is destructive, so if it sees something, like you don't want to accidentally run init on an existing one because it just overwrites it. So if you make a mistake, yeah, so be warned that maybe there should be like a force flag in there where it would warn you otherwise. But yeah, now it's installed it and it's actually running. I can create a database. And I can run commands like, I'll just do it manually, sorry. Create table T1. Now, if I don't specify a distribution clause, it'll just pick a reasonable one. If there's a primary key, it'll try to use it. If not, it will look for, say, a unique key, and so on. So if I create a few values here, I'll turn on timing so you can see it's actually pretty fast. So this is querying across two data nodes. We have this other command called execute direct, which is pretty handy. So you can kind of bypass the coordinator planning. It's really, you don't want to give your regular users this, but for the DBA, it's useful to see what's going on. So you can see data node 1 has 2 of the values, and data node 2 has the other value. We can also do things like add coordinators. Here's a little command, add coordinator. I'll initialize that. So I'm bringing up a second coordinator to our 1 coordinator 2 data node system. It's going to go through. And now if I run psql and connect to instead of using the default port, I'm using the second coordinator's port. It can also see all the data. Yeah. Okay. Any questions about that?
So what does /d look like?
How the schema says storm catalog, it's showing that's where we lock down for concurrent users. We do a little trick there with the namespace stuff. I'm kind of getting low on time. I just wanted to jump ahead to some other stuff here. One moment, please. I'm going to step through these real quick because I'm running out of time. Oops. Sorry. So we also get asked a lot, okay, what about this Postgres-XC thing? How does it relate? Well, we do share a lot of code. Some of the basic infrastructure is the same. But we added some of our own enhancements. The planner and executor are quite different. But you know, we have a lot of the same developers, a lot of the same original XC developers continued on with XL. We have the GTM pooler catalog. A lot of the things are the same. But there are some differences. We've enhanced performance. We have data node to data node communication that speeds things up. We avoid reparsing, sequences optimized, security, we collect additional statistics, and our planner and executor are different. We also have a set of different configuration parameters to allow you to tune this stuff as well. The code, if you look at it, it's pretty identifiable to see which part's XC and which is XL. If you look at it, I apologize for going so quickly. In terms of community, you can go to postgresxl.org to get the code. And I'll set up a mirror. Docs are also online. We really want to emphasize stability and bug fixes over features and be focused on performance and have a really open community. So if you want to get involved and contribute, great, come join us. You know, we want to model on the Postgres community in terms of major contributors, core, and all that stuff. So I encourage you to do that. Today it was asked, could this be a contrib module? Or recently it was asked, yeah, I think we could make, it would be difficult and we would need new hooks, but this might be something we should look at some point, making this a contrib module. I think that may help it gain more interest in the community. Our roadmap. Right now we're working on improving cluster management, that PGXC CTL utility that was demonstrated earlier. So look for a new version very soon. We want to catch up, as I mentioned, on Postgres itself, up to 9.4. And an area of focus is going to be making it better for analytical platforms. Like Postgres has these awesome foreign data wrappers. We want to allow those to be distributed so that you could pull in, if you have an external data source that it itself is also sharded, we could handle it in parallel. That makes it so for compressed column stores, things like that that are external, that we could access that and do it in parallel. Also, we're going to look at making GTM optional if you're doing this for data warehousing and you're not so you just have a bulk load setup. You know, we can perhaps set up a simpler architecture. And then high availability again. Any questions in the 10 seconds I have? Yeah. I stand behind it. I mean, we have this cluster called StormDB that's essentially been running with this code for like a year and a half. There have been hundreds of databases created on it. We've shaken out issues on it. I encourage you to try it out and see if you can break it. Yeah. I would use it. Yeah. Any other questions? And it is in the process of being deployed, and I'm soon going to be doing a training in Spain at a customer, and then another one in California. Yeah, I encourage you to look at it.